Welcome to Opgal's OGI Academy. I'm Dr. Ram Hashmonai, Principal Innovation Scientist here in Opgal, responsible for the research and development program here in Opgal. What is OGI technology? I brought here two examples of movies taken by this camera here besides me. The one on the left is a methane leak that is in industrial facility. We can see we have leaks here in the center of this circle over here, but we can see that we have leaks in multiple points here around this pipe. The other leak is, or emission, is from a storage tank, and we can see here on the sky background emissions of some kind of volatile organic compounds that are emitted in these images. So, optical gas imaging technology is essentially a thermal imaging camera. We have two regions of spectral regions of thermal imaging. We have the mid-wave IR. So optical gas imaging technology are thermal imaging cameras that working in two spectral regions. One is the mid-wave IR and one is the long-wave IR. We can see a spectrum of methane absorption here in the mid-wave. These are the absorption coefficient curve of methane in this range, spectral range, and here we see it around 7.7 micron, which is in the long-wave IR. Until recently, when we said optical gas imaging, we meant only this portable, cooled mid-wave IR infrared camera. We chose this region and this cool camera because we wanted to detect very small leaks of hydrocarbons, volatile organic compounds, including methane, and all of these compounds absorbs in the mid-wave IR, so we can use this one for detecting them. So this cooled mid-wave IR camera that I have here on the desk is a very sensitive camera. We call it the IC Gas 2.0. This is our second generation, and they've been around for quite a while. They've been around since 2006, and they are already in American and all over the world regulations for leak detection and repair programs. So recently, this field of optical gas imaging has evolved to include also fixed cameras that are installed for 24/7 year-round detection, automated detection of gas leaks. And we have on this family of cameras, we have on the fixed one, we have one that is in the mid-wave IR and one that is in the uncooled. All of these cameras that I show over here can see methane. This is the common denominator of all of these cameras. So long-wave IR camera, we have also a newly developed portable one. We call it the IC Gas Mini. So all of these gases, all of these cameras are detecting gases, and there are several trade-offs between these technologies, but they are all called OGI technologies, all of these cameras. So We mentioned the long wave IR, which is between 7.5 micron to 14 microns, and the mid wave IR, the MWIR, which is between 3 and 5. There are several trade-offs between this type of cameras. We can see that the mid-wave cooled cameras are high sensitivity, where the LWIR cameras are more moderate sensitivity, and the specificity of the MWIR, we have no specificity actually in the MWIR. We can see VOCs. When we detect a gas leak with the MWIR camera, we don't know if it's methane or other hydrocarbons or volatile organic compounds that are leaking from that component. But when we look at LWIR camera, either if it's a fixed camera or a portable one, NL camera, we can see that we can have cameras for specifically for methane or sulfur hexafluoride or ammonia here. But I need to mention here that sensitivity in this camera is less sensitive than the MWIR camera, and we cannot see all VOCs with the LWIR camera. So the typical optical gas imaging camera is a regular thermal imaging camera, that the only difference is that somewhere between the lens and the detector, we install a bandpass filter that transmits energy in the absorption features that I showed you in the previous slide of the target gas. So let me start deriving the OGI equations. I'm apologizing here for being heavier on the physics and math. Just get the bottom line for what I'm trying to show. That's why I added graphs and graphics to lighten up this lecture. So, in order to understand what is spectral radiance, we need to know that everybody in nature, it doesn't matter if it's a solid, liquid, or even gas, emits energy that is a function of its temperature. And the spectrum of this graph, which I mean the spectral radiance intensity, or the energy as a function of wavelengths, is described by Planck function. This is the equation. We can see that it's a function of the wavelength and the temperature and a bunch of Planck coefficient. We have the speed of light here. We have the Boltzmann coefficient here, the K here, KB over here. And when we calculate this as a function of wavelengths and temperature, we get these three curves. I calculated these at 50 degrees. Here, this is the gray curve over here, and at 25 degrees, and in 0 degrees Celsius, centigrade. So, several observations about the spectral radiance Planck function that we can see. We can see that the higher temperature curve will always have higher or more energy emitted at the same wavelengths, at any wavelengths. So it doesn't matter which wavelengths we detect the energy. If it has higher temperature, it will have more energy coming to the detector. So that's one observation. And we can see that the intervals here are 25 degrees between these curves, but the spaces at any wavelengths are not equal. So another observation, that this change with temperature is not linear between different temperature. So the difference in the spectral radiance between 0 and 25 degrees is not the same as the difference between 25 degrees to 50 degrees. The last observation that I wanted to show you over here, and I chose the infrared thermal imaging region, which here we have the MWIR region, and here we have the LWIR. I'm sorry for my handwriting with my mouth. So what we can see here is that the peak, the maximum wavelengths, or the wavelengths of maximum spectral radiance for each curve is showing up in a slightly different wavelength. Here it's over here. So I would say here it's about 8.8, and here it's around 9.8, and here it's about 10.8, something like this, 10.7. It doesn't really matter. So this is my last observation here. It brings me to Wien's law, Wien displacement law. I write it over here. Wien, actually it was German, probably it was Wien law, not Wien. So Wien's law says that lambda, the wavelength, max, times temperature equal constant. This constant is around 2,900, and the units are Kelvin times micrometers. The reason I'm telling you this, 50 degrees is about 323. If you multiply by 8.8, you get about 2,900, and you multiply 298 Kelvin by 9.8, you get the same number of 2,900 Kelvins times micrometer. So this is the Wien's law. So if we want to maximize the spectral radiance, we need to choose a spectral region when it's and the temperatures. We can use this law to understand where do we have the maximum of this spectral radiance curve. The last thing that I want to mention in this slide is that this graph over here are spaceborne satellite observation of the Sahara Desert in the summer, where middays. And the 320, it's almost 47 degrees here. Looking 47 degrees and looking at Earth and the atmosphere, 47 Celsius. And you can see the curve of the 320 Kelvin, which is equal 320 Kelvin. I'm sorry for the handwriting. We can see that between 8 and 12 microns, except for the ozone layer here that absorb the radiance that come from the Earth, we can see that this curve of the 320 describes very well the measured, the observed radiation, like the Planck function. So I wanted to mention the atmosphere because it's all related to the next slide, that we are talking about a radiative transfer model for describing the OGI equations. So what is a radiative transfer model? You can see the one-layer radiative transfer model that describe here on the figure here on the right here. The atmosphere is a layer. The background here is the surface of the air. And it's described the energy budget, the thermal energy budget that coming from the sun, return to space, absorbed by the surface of the Earth and then emitted in the long wave IR, absorbed by the atmosphere. The atmosphere is the black body itself, and it emits energy and absorbs energy, and the higher concentration of greenhouse gases that we have in these layers, it absorbs more and less going back to space, and that's why we have the global warming effect. And all of the models, all the climate models are actually radiative transfer models. So we're going to use a similar model to describe the OGI technology. So the radiative transfer model is actually an energy balance of thermal electromagnetic radiation that comes from the background, which is, we can describe it over here with the letter B. This is the Planck function as a function of the background. This is this layer. And the gas plume that in the middle has the thermal energy of the gas. I'm sorry, this is the T, the temperature of the gas, and this is the temperature of the background. This is the Planck function. I hope it's now clear. And here we have the air, we call it the foreground air atmosphere between the gas plume and the OGI camera. And this is as the spectral radiance as a function of the temperature of the air. Okay. Now, these layers transmit, each of these layers transmit this energy, but it's also this layer. When this energy leaves this layer into this layer, it's also being absorbed by this layer, and we need to write here tau of the gas. And here we have the tau of the air. This is the transmission of this layer and this layer. So if we are now trying to see what will be the radiance, the spectral radiance that will reach the camera from the background, and we write it from left to right, it's going to be this spectral radiance that comes from the background times the transmission through the gas layer and the transmission through the air area. This is the gas layer transmission emission as the Planck function with the temperature of the gas, but it needs to go through the air on its way to the camera, so we need to multiply by the transmission of the foreground air layer. And we need to subtract here the absorption of the gas layer of what's going on over here. So this is subtracting the absorption. So we multiply by the transmission, which is the absorption, and then it goes through the air to the other layer. And we have the foreground air layer, and this is the transmission, this is the emission, and this is the absorption of whatever this layer absorbs. So if we rewrite this equation, we get that in the presence of a gas plume, this radiative transfer model will give us the spectral radiance that reaches the camera from the atmosphere. Okay, so this is the spectral radiance when we have the gas plume between the background and the camera. But when we have no gas, we can see that the transmission of the gas is equal to 1. Okay, so we are left here with only this term. And this term is equal to 0. It's gone. And we are left with this term. Okay? So because of the temperature of the gas there is no gas, so we have no this layer. So this is the term of the gas plume, this is the term of the background, and this is the term of the foreground air. We divided this to these three areas. So if we take the difference, what is the contrast? The contrast that reaches the camera lens. The contrast is the spectral radiance when we have the gas, when we don't have the gas, minus the spectral radiance when the gas plume is present. And if we write the two equations from the previous slide over here and rearrange it, we can see that this is the transmission of the foreground, and when we are very close range into the gas plume, this is maybe assumed equal to 1. Okay, and this is depend on the atmospheric transmission. It could be water vapor, it could be the gas itself, like methane, CO2. It could be particulate that contribute to this particulate matter that contribute to this transmission tau of the foreground air. And this is derived from the Beer's law, that says that the transmission is the exponent of the absorption or extinction coefficient times the concentration of the substance times the path length through the plume or the air. So, and we are left here, when we take these two equations, we are left with what we call the general OGI equation of spectral radiance, and we'll have here what is the contrast that we'll detect here in the camera as a function of the temperature of the background, temperature of the gas plume, which is the air around the gas plume, 1 minus tau of the gas, which is the transmission of the gas layer. And we can see that inside this transmission, it's dependent on the concentration of the gas. This is the absorption coefficient of the target gas. It could be for methane or for butane, it will be different curve, but the concentration is the most important. We can see here that the concentration is 0 here. The exponent comes to be 1. So the transmission is 1. So it goes, when we have no gas, we have no layer, it just goes through this like it's part of the foreground air. And when this concentration go larger, this become this is going to be a number that is, because this exponent is negative, we will get numbers that are between 0 and 1. And when the concentration is very, very large here, we will get the transmission is 0. No spectral radiance will go through this layer. It will be all absorbed by the gas plume. So we talked about the radiative transfer model of the atmosphere, but we need to understand that for each target gas, we will put different type of bandpass filter to actually have the transmit the radiation where the gas is absorbing the electromagnetic radiation, thermal radiation. So what we have here is, if we look at this graph on the left, we have again the example of methane, which is the most common compound that we measure both in the long wave IR and in the MWIR, in the mid-wave IR. We can see here that the methane here is in the mid-wave IR is absorbing between 3.15 to 3.48 microns, and we have here the specific lines. And what we are doing here, we are actually integrating between the absorption coefficient through the 1 minus the transmission of the gas. So let me remind you that the target gas transmission is tau of g is this exponent, and we take 1 minus of it to describe the absorption, not the transmission. The transmission, 1 minus the transmission is the measure of absorption. So we integration the absorption coefficient, but we including the concentration, and we calculate it between the beginning of the filter lambda 1 to the end of the filter lambda 2. And we calculate this integration. The spectral radiance of the background and the gas is pretty much constant, and the difference does not change much when we do this integration. And what we get is what we call a camera specific or compound specific OGI equation that include the integration through the filter. And I want to show you that this over here, it's a compound specific response of that camera, and it depends on the transmission of the filter that is installed inside the camera. So if we calculate this value, you can see the value as a function of wavelength. You can see that for different concentration, we have the red curve is 10,000 ppm meter, actually integrated concentration. We are talking about the product of concentration and path length through the plume. This is the product of the concentration times the width of that plume. 10,000 ppm meters, we get the red curve. But if we increase it to 100,000 ppm meters, we get the green one. So we can see that this is a function of concentration, this response factor, and we can use this later for quantification and calculate sensitivity. And this is what we called the CSR, the compound specific response. I took this integral that actually integrate 1 minus of the transmission through the filter times the filter transmission integrated between the two wavelengths, the two edges of the filter. I call it compound specific response. And what I show here on the left is that for different compound, first of all, it's not linear, and these values are actually a function of the concentration, and the response is not linear. This very not linear. If you can see over here, this axis, the x-axis, is actually logarithmic here. And still we can see that both of them are not linear, but they are not linear in a different way. And it's all about how the compound absorption coefficient is situated inside that filter. So if it's fully absorbed, fully centralized inside the filter, like the methane, you can see that it will respond similarly to that curve. But if it's only partially, it will get saturated, so it will go this way for propane, which part of this absorption coefficient curve of propane is outside, and we will see it in later lessons how the difference between different compounds affect the response and sensitivity and range of these compounds. To summarize, I wanted to show you that the OGI equations are derived from a simple two layers radiative transfer model, that each layer is assumed to have similar characteristic, constant temperature, constant concentration of the gas, constant width, the same width, so we can separate it and we can derive this equation, explain the contrast that we see on the camera in the presence of gas, and also use all of these equations to later on derive the actual concentration of these gases, quantify the concentration, and even quantify the mass flow of the gas leak. Now that I concluded the description of the first lesson, I would like to encourage you to contact us with any questions, and also let you know that we have infographics that describe the material that has been presented over here. We have a document, a monograph that discusses this in details and go through the derivations in details. We have also this presentation that we can share with you. If you want us, just contact us at info@opgal.com. Thank you, and see you in the next lesson.